Hess's law is a crucial law in learning the enthalpy cycle. It states that the enthalpy change of a reaction is independent of the route taken. This may sound puzzling, but it is actually not difficult to understand at all. Take a chemical reaction where the reactant A becomes product B, and let the enthalpy change of the reaction be delta H. The chemical process of directly turning the reactants into the desired products is called the direct route. Suppose there is another way to approach the same products. Reactant A first forms compound C, which then turns into product B. We will assume this is route 1. The enthalpy change of the reaction of reactant A turning into compound C is delta H1, and the enthalpy change of compound C into product B is delta 2. This is where Hess's law takes place. The enthalpy change of the direct route of turning A into B is equivalent to the sum of all the enthalpy changes of chemical reactions taking part in route 1. Consider another route that turns reactant A into product B. A first turns into compound D, and compound D turns into compound E. And finally, compound E turns into our target product B. We will name this as route 2. Similar to route 1, we will assume the enthalpy change of the reactants being delta H3, delta H4, and delta H5. Although the chemical processes involved in route 2 and 1 are very different, Hess's law suggests that the total enthalpy change of this reaction stays constant. So the sum of delta H3, delta H4, and delta H5 are equivalent to delta H. This is because all these reactants ultimately lead reactant A into product B. You can think of this similar to vectors, but instead of coordinates, the reactants and products act as nodes and the enthalpy changes of each reaction as the modulus of the line connecting the reactants and the products. As long as the starting point and the ending point remains unchanged, the enthalpy change of the reaction, or the modulus of the vector, stays constant. Enthalpy cycle is a visual way of representing different approaches to turn reactants into products. By drawing and using enthalpy cycles, we can calculate enthalpy changes of chemical reactions. Let's first imagine a chemical equation. The reactant turns into product 1. The enthalpy change of this reaction is delta H. Assume another compound, product 2, that can be created with both the initial reactants and product 1. The substances at the origin of the arrow represent the reactants, while the substances of the arrow side represents the products. The enthalpy changes of initial reactant to product 2 and product 1 to product 2 will be A and B. In this scenario, suppose if we were given the exact numbers of A and B, and the target is to find delta H. First, we need to find an approach of turning the reactant into product 1. If we assume the chemical reaction of product 1 and product 2 being reversible, we just found a different route to turn the reactants into products. We can deduce from Hess's law that the sum of the enthalpy change of reactant to product 2 plus the enthalpy change of product 2 into product 1 the same as delta H. The enthalpy change of the first reaction is given being A. We do not know the enthalpy change of the second reaction, but we do know B, which is coincidentally the enthalpy change of the reversed reaction. Therefore, the enthalpy change of the reaction of product 2 and product 1 is simply the opposite of its reverse reaction, which is negative B. We then total up the enthalpy changes and get delta H, which is A minus B. Assume a second scenario, but unlike the previous cycle, the arrows are reversed. How to find delta H in this scenario? Same as the previous problem, we first find an approach of turning reactant into product 1. Instantly, we find the approach of first turning reactant into product 2 and product 2 into product 1. The enthalpy change of reactant into product 2 is calculable as the enthalpy change of the reverse reaction is given. We add a negative sign in front of the enthalpy change between product 2 and reactant, which is negative A. Then total up the enthalpy changes involved in the approach, giving delta H a value of B minus A. This is all for this video. Thank you for watching and subscribe for more A-level chemistry videos.